Let me welcome you to this workshop, Math When They Don't Understand. Psalm 119 and verse 18 says, "Open thou mine eyes, that I may behold wondrous things." I'm sure as the supervisor you have prayed many times, Lord, open their eyes. They can't see what I'm trying to explain to them. And I want to help you do that today, but also I want to help you help your students understand mathematics so that they can appreciate the wondrous things that God has done in the world. As educators, we often forget that the goal for our students is understanding. We want to help our students to understand both the why and the how. And that starts long before the flag ever goes up. It's often possible to learn the how mechanically without understanding why it works, why it is that way. Procedures that are learned that way are often forgotten very easily. Understanding the why helps them with the how, because the how then makes sense. I'm going to divide this workshop into two parts, if you will. The first part I'm going to call Foundations for Understanding, and the second part is called Tools for Understanding. The first foundation for understanding is we want to create a conducive atmosphere. Your students' attitude towards math is a reflection of the staff's attitude towards math. For a supervisor, for any staff member for that matter, to say something along the lines of, "I've never been good at math," or "I don't like math," or "math is too hard," is to throw water on any interest in math in their students. If you think math is too hard, if you say it's too hard, then it's going to be too hard for them. But the question is it too hard for you, or is it too hard for them? You want to make sure that you properly diagnose your students. This will eliminate any learning gaps that they may have in math. They must have mastered the basics of math before they can progress. Many students develop math problems in the middle levels because of a failure to master the basics. So in their paces, you want to make sure that they read the learning strips and directions for each section of the pace first. The old adage, when all else fails, read the directions. These self-instructional learning strips include explanations, examples, and student-completed activities. There are activities contained in those learning strips and in the directions where the student has to answer questions and complete those activities and then score them. That forces them, as it were, to read those directions in those learning strips. These interactive instructions will engage the student in learning and keep him from skipping over those learning strips. It's important to help a student realize that if they slow down and concentrate on the teaching material and examples, that they will actually end up gaining a better understanding of the new concepts and actually be able to work through the pace more quickly. It will also reduce the number of Christian flags that you as a staff member have to answer. Then we want to make sure that we facilitate mastery of the concepts. Our curriculum is mastery-based. But that mastery does not happen, it will not happen unless you as staff ensure that it does. There are occasional yellow supervisor initial boxes in our PACEs, asking the supervisor to check for comprehension or understanding of the concept at hand. Or maybe it's the memorization of basic math facts. Before allowing a student to continue, you need to ask them questions. If it has one of those yellow supervisor initial boxes that says check for understanding, don't just stick your initials in those boxes and allow the student to proceed. They need to be asked questions. Maybe give them a sample problem to work so that they can prove to you that they do in fact understand the concept on that page. Because chances are there's going to be a concept just a few pages down in the pace that the child is going to need this concept in order to understand that concept. And if you've not ensured they've mastered this concept, guess what happens when they get over there? You're going to have to back up and deal with this concept before they can proceed. Mental mathematics are still necessary, and students need to drill those basic math facts. Math facts in the elementary levels, mastery equals automaticity. Students should always practice by saying the whole problem and the answer aloud. When the pages in the lower elementary pages where they have to do basic addition facts or basic multiplication facts, you want them to have the point of mastery where they can automatically say those facts without even thinking about it. And you want them to have to say the whole problem. 7 times 8 equals 56. That is what is called a verbal chain. As a result of this kind of practice, the student, whenever they see or hear 7 times 8, they're going to think 56 just like that. And students who do not master these basic math facts when they are younger will face discouragement every day in their math goals, all the way from elementary school through middle school through high school. They're discouraged every day because they don't know those math facts, and as they do their math goals, they're going to be more prone to cheat. And by that I mean they're going to misscore. Let me illustrate that for you. If a student is doing a 4-digit number times a 4-digit number, did you realize there are 26 separate individual calculations to successfully complete that problem? And every one of them is a basic math fact. It's a single-digit number times a single-digit number, and then adding a column of numbers to get the answer. If they do not know those basic math facts, they're going to be frustrated. Imagine if they had 10 or 12 of those kind of problems on a single page. And if they don't know those basic math facts, they're going to get those problems wrong, and they're not going to want to redo the whole problem. They're going to go to the scoring station, they're going to find out what the answer is, and erase the answer and not rework the problem. So you want to drill and drill and drill those basic math functions. And if you have a student, as you're working with them, if you have a student who shows a weakness in an area, their 9 tables or their 7 tables, it would be prudent for you to stop and spend a few hours or maybe a day or more. Don't give them any math goals that day. Give them Math Builder, give them flashcards, give them practice sheets until they can demonstrate mastery of whatever it is that they are lacking in. Because as the adage goes, it's never a waste of time to stop and sharpen their axe. So if they don't have math goals for a day, but they master that concept that they're missing, it will be time well invested. And then next, you want to make sure you capture the flag. Children need many opportunities to develop and practice math skills in a threat-free environment. What do I mean by a threat-free environment? Well, it depends on how you answer their flags. If they feel like they can answer a flag or put up their flag and say, I need help with this or I don't understand this, and not feel threatened, this will encourage them to ask for help when they need it. If they feel threatened, then they won't ask you for help, and they're going to get those answers one way or the other. They're going to use a calculator when they're at home, they're going to get their big brother to do their math goals for them, or they're going to cheat in some other way. So we must go, as staff, we must guard our attitude when we're answering a flag, especially if we're answering that flag for the 5th or the 8th or the 10th time for the same concept. We need to watch our words, our facial expressions, and our body language. A supervisor's words and actions are powerful motivators, either positively or negatively. If we've answered the same flag, same student's flag for the 10th time, and we look over their shoulder and we see, oh no, it's that same thing again. Did you know that children can hear you roll your eyes? If you walk up behind a child and do this, you didn't say anything. You didn't say anything verbally. You uttered no words. But the student can feel your disgust, the fact that you're unhappy with them. And children, they want to please you. They want to please you as their supervisor. But learning takes place best in an environment that is perceived by the student as being safe. When a child does not feel that sense of safety, their brain goes into survival mode when they feel threatened by the supervisor. And when they're in survival mode, the active learning parts of the brain are actually neglected, making it even more difficult for a child to understand a concept that they're already struggling with. As a supervisor, you must believe in the student even when he doesn't believe in himself. You need to expect them to achieve the most from their learning. And then as you're explaining a math concept to the child, you need to realize that and tell them to take one step at a time. The child needs to realize that learning math is a developmental process that takes time and practice. Learning math is a linear process. In social studies or history, they can study the 18th century before they study the 17th century. They can study English literature before they study American literature. It doesn't make a great deal of difference. That's not true in math. Math is a line upon line, precept upon precept, one concept building upon another, and it must be done in order. And then in their math goals, you need to require them to show all their work. They won't want to do that. They're going to say, I want to get my goals done. And it takes too long to show all the work. But you need to require them to show the work because that shows complete understanding on the part of the student. And it's easier for you as the supervisor if the child gets the problem wrong and they ask for your help, then you can say, oh, look, you were right down to here, but you made a mistake with a sign here, or you left this number out. As opposed to the fact that they show no work at all, you have no idea what they did wrong, neither do they, so both you and the student have to go all the way back to the beginning of the problem and start over. Avoid letting a child do multiple steps at the same time. Have them write each step of the solution to the problem, especially when they're beginning to learn it. If they try to combine steps, it increases the chance of them becoming confused. And then you want to address technical problems. Technical problems are personal habits. In math, neatness counts just as much as it does in English. For example, you want to make sure when they're learning how to add columns of numbers that they keep their columns aligned vertically. Or when they're learning multiple digit multiplication, they need to align their columns vertically. For younger students who are having trouble with that, you can purchase large grid graph paper and have them put one number in each box so that they are forced to align those numbers, because if their columns are off askew, they're going to get the wrong answer because they're adding the wrong number to the wrong number. When they learn about decimal fractions, they need to align their decimal points vertically, or they're going to get the wrong answer. Again, they're going to be adding or subtracting or multiplying the wrong number from the wrong number. They need to be trained and forced to write their numbers and their variables neatly. Make sure that they are able to distinguish between their 1 and their 7 and a lowercase l, and also distinguish between a 2 and a z. They can use the crossbar on the 7, as European countries do, to make sure that they know that's a 7 and not a 2. And they can use a lowercase cursive l for a lowercase l for a liter, for example, so they know that's an L and not a 1. I had a student some years ago who was learning how to solve simultaneous equations in algebra with two variables. And she was writing very quickly, and when she wrote her y's, she went all the way through the second line of the y so it looked like an x. And she had combined all of her variables as if they were all x's. And she put her flag up and said, Mr. Dawson, I lost my y's. I don't know where they went. And it was simply a matter of penmanship. Make sure they begin a solution with plenty of room. And that when they're solving an equation, they do one step per line. Sometimes they'll want to put two steps on the same line to save space, but then they can't tell where one line stops and the other line starts, and they are confused as to what is done in that step. When solving equations, they need to align their equal signs vertically, because sometimes there's going to be more on the left side of the equal sign and sometimes more on the right side of the equal sign. In math and in science, both, when they are solving a problem that requires a formula, require them to write that formula every time. That's the first step in solving that problem, is to write the formula that they're going to be using, whether it's area or volume or interest or the quadratic formula. That way, that helps the student commit that formula to memory, and they automatically associate that formula with that kind of problem. Oh, this is an interest problem. This is the formula I use. This is a quadratic equation. This is the formula that I use. And then, in like manner, when they are in geometry in high school and they're completing their geometry handbook, make sure they write out those definitions, those axioms, those postulates, and those theorems in full in their geometry handbook. That act in and of itself is a good learning tool. And then when they're doing a geometric proof, have them, when they're giving the reasons for each step in their proof, to write out, again, that axiom, that postulate, in full, not just give the number. Because there's no universal numbering system for geometry theorems or axioms. So what could be Theorem 37 in our curriculum could be Theorem 10 in someone else's curriculum. So they need to know what the theorem actually says, and if they write it out verbatim each time they do a proof, number one, again, they'll learn that theorem and they'll learn what situations that theorem is applied to. And then you want to require your students to use proper mathematical terminology. You need to acknowledge, and then they need to acknowledge, that math is a language all its own. It's full of definitions, vocabulary, symbols, and notations that students must know in order to succeed. It can only be mastered with practice, as if when you're learning any other language. You want to make sure that they call it an exponent, not the little number up in the corner. That you have two addends in an addition problem that equal a sum. They have a subtrahend and a minuend in a subtraction problem. They have a divisor and a dividend and a quotient in a division problem. A multiplier, multiplicand, and a product in a multiplication problem. They need to learn to call things by their proper name. And one way that you can ensure that that happens is require that they do it, and also when you're speaking to them and you're helping them with their math problems, to use the terminology correctly. And then I want to encourage you to mix music and math. Now, I'm not talking about the fact that music is inherently mathematical, and I'm certainly no musician. But what I mean is that mathematicians, almost without exception, have noted that the best environment for doing difficult math problems is either a quiet place. Sir Isaac Newton developed the calculus sitting out under a tree. It wasn't gravity he was working on out there and the apple hit him in the head. It was calculus he was working on out there. So mathematicians say difficult math should be done in either a quiet place or listening to Baroque music, such as that by Bach, Vivaldi, or Handel. This is because Baroque music is very orderly and is without attention-grabbing climaxes. So you might consider playing this kind of music very softly in your learning center. You have a byproduct also, they'll develop an appreciation for a type of music that they probably wouldn't listen to under other circumstances. So now let's turn our attention to tools for understanding. And this is the more fun part of this workshop. You want to make sure that when they solve a problem and they get an answer, that they take a reality check. They need to ask themselves, does this answer make sense with what I was trying to accomplish, with the numbers that I was using? Is their answer reasonable? Now, your students would never have to do this. But an example I often use is, suppose they had to find the mass of a squirrel. And their answer is 1,970 kilograms. They should be able to look at that answer and go, I must have done something wrong. They can't possibly be right. Because the mass of the average adult is 68 kilograms. And if they have a squirrel that has a mass of 1,970 kilograms, that is something that you need in a horror movie. And then reasonable speeds when they're working distance, rate, and time problems. For example, 40 meters per second is roughly equal to 80 miles an hour. So if they're working on the speed of a train or the speed of a truck, and it's 675 meters per second, I don't want to be in that train or on that truck, thank you very much. And then when they're working algebra, does their answer make sense algebraically? They need to look at what they've done and said that they didn't divide by 0, or they didn't take the square root of a negative number, because you can't do either one of those things. And then in math and in science, they need to specify the units. A measurement is always a number plus the units of the problem. Units, many times, students will want to put the units aside, do the calculation, and then stick the units back in. It's very easy for them to make a mistake if they do that. When they're younger and they're converting from liters to kiloliters or millimeters to centimeters, or even from bushels and pecks to quarts and gallons. And sometimes they have to, in order to do that, they have to borrow in order to subtract or carry when they add. And if they leave the units out, they're not going to know when they need to do that. And you need to train your students that if the answer is 17 centimeters, 17 is not the correct answer. The correct answer has to be the number and the units. And then when you're working with students, don't be afraid to draw diagrams to help them understand, or illustrations to help them understand, or to demonstrate concepts on a piece of paper. I would be a very wealthy man if I had a nickel for every pizza I ever drew on the edge of a paste page in order to help a child understand fractions. Or if they're doing distance, rate, and time problems, for example, draw a little diagram. This car left at 3 o'clock and it drove 40 miles an hour, and in 3 hours it's here. This one left at 5 o'clock, he's driving 50 miles an hour. So they can visualize, they can see what it is that they're trying to solve. In geometry, when they're doing a geometry proof, they are given certain things, certain information. Train them to mark on the diagram what they've been given. If 2 lines are congruent, to mark those 2 lines with a single line through each one to show that those are congruent. Or if 2 angles are congruent, to mark those so when they look at the diagram, they know what they've been given, and then they can use that to figure out what it is they're supposed to prove. It helps students see what they're being asked to do. And this is fun, to use mnemonics with math. And mnemonics are simply memory devices, things that help us remember things. And the sillier they are, the more effective they are. So you can create silly sentences. Now you may have, one thing a student's going to need to learn is the order of operations in mathematics. The order in which you do things is important in order for you to get the correct answer. So one way that someone came up with to remember the order of operations is, it's an acronym. They say PEMDAS, P-E-M-D-A-S. Well, PEMDAS is kind of boring to me. I like, and I've used with students, please excuse my dear Aunt Sally. Please excuse my dear Aunt Sally. When the order of operations, they remove parentheses first. That's the P. Then they deal with the exponents. That's the excuse. Then they multiply first, left to right. That's the M. Then they divide left to right. That's the D. Then they add left to right. That's the A. And then they subtract left to right. That's the S. They can remember the order of operations. Please excuse my dear Aunt Sally. And when students are learning the metric system, and they need to know, especially when they're converting from one unit to another, they need to know the graduated order of those metric prefixes. Which ones are larger and which ones are smaller, because if they're, depending upon what they're doing, they're going to either multiply or divide. So a way that a mnemonic they can use to memorize or remember those metric prefixes is King Herod died Monday drinking chocolate milk. King Herod died Monday drinking chocolate milk. The king is the K, that's the kilo. Then Herod, that's hecto. Died is the D, that's the prefix deca. Monday is the M, that's meter. Drinking is the prefix deci. Then C is chocolate, that's centi. And then M is milli. So they know that the order of the prefixes, the middle one there, when I said meter, that would be the meter or the liter or the gram. But they know the order, so they know whether they're going to move the decimal place however many places to the right or how many places to the left, depending upon when they are multiplying or dividing. Now, quite frankly, it's rare that you hear of a decameter or a decimeter. You don't hear those measurements often, but they need to know that those prefixes are there so they move the decimal place the proper number of times. And then you can design colorful diagrams. Many students have trouble with problems that are involving percents. So I've developed this triangle that has the letter P at the top, and then the bottom left corner is the percent sign, and the bottom right corner is the W. The P is the product, the percent sign is the percent, and the W is the whole. So if they need to find the part, the P, that's at the top. So they're going to multiply their percent times the whole in order to get the part. If they need to find their percent, they're going to divide the part by the whole, and that will be the percent. Or if they need to find the whole, they can divide the part by the percent. Very simple tool to help them remember what order they do things in. And similarly, with a distance, rate, and time problem, another triangle where you have the letter D at the top of the triangle, the letter R, the lower left-hand corner, and the letter T at the lower right-hand corner. D is distance, R is rate, T is time. If they're given the distance, then they multiply the rate times the time. If they're given the rate, they divide the distance by the time. If they're given the time, then they divide the distance by the rate. And this is where you can have a lot of fun. I want to encourage you to illustrate concepts. Whenever new material is presented in such a way that students see a relationship between concepts, it generates greater brain cell activity and actually achieve more successful long-term memory and storage. For example, we tell students they memorize the definition from their PACE and they put it out on the answer on the PACE test. That pi, mathematical pi, is a relationship between the circumference of a circle and its diameter. Well, that sounds nice. What does that mean? But we can take any round object. This is just a paper plate. Actually got from the break room down the hall from my office. And then I have a roll of paper here off of an adding machine. Some of you don't even know what an adding machine is, but just any strip of paper. And you put the plate down and you put the strip of paper around the edge of the plate and mark where the two ends meet. Actually, I did that, and there's a mark on my strip of paper here. That is the circumference of that paper plate. Then you take a ruler and measure the end from the end to the mark on the paper, and that is the circumference of this plate. And this plate has a circumference of 21.1875 inches. I changed it to decimals to make the mathematics easier. Then you take the same paper plate, lay it flat, and use a ruler to measure from one edge of the plate to the other. That's the diameter of the plate. And mathematical pi is the circumference of a circle divided by its diameter. So that plate has a circumference of 21.1875 inches and a diameter of 6.75 inches. You divide 21.1875 by 6.75 and you get 3.13388. Mathematical pi is usually written as 3.14. So just using a paper plate and a strip of paper, I got really close to the accurate number for mathematical pi. That makes sense to the student to go, oh, now I know what you're talking about with pi. And then you can tell the students, because pi is a relationship between a circle and its diameter, that when they're working with geometry formulas, if it's round in any way, it's probably going to have pi in it. If it's a circle, if it's a sphere, if it's a hemisphere, if it is a cone, anything that has a round face to it, the formula is probably going to have pi in the formula. And then you can use tools like this to demonstrate place value. Now remember, I began the workshop with saying sometimes it's possible for a child to learn the how of a concept and not understand the why. When I was in elementary school and I was learning how to add with carrying, I could do it mechanically. I knew that I added 9 and 7 and I couldn't write the 16 there, so I would write the 6 and I'd carry the 1. I put the 1 at the top of the next column and add it in. And similarly, when I subtracted, I knew that I couldn't subtract 9 from 7, so I would borrow from the number next to it, draw a line through that, reduce it by 1, and put that 1 next to the 7, then I could subtract 9 from 17. I could do it mechanically, and I could get the right answer. But I had no idea why I was doing what I did, because until I learned place value, I didn't understand when I was carrying that 1 in the addition problem, I was actually carrying a 10, because I put the 1 at the top of the tens column. Or when I was borrowing a 10. So that's why the 7 became 17. So you can use, there's many ways that you can explain place value to children. This is for younger children. We have straws, and I've illustrated the number 136. So there's 100 straws in the 100s place, there's 30 straws in the tens place, and 6 straws in the ones place. Now, if I were going to if I was going to add another bundle of 10, I would put it here in the ones place, but then I'd have 16. So I would take those 10 straws and put a rubber band around them and move them to the tens place. I was carrying a 10. And you can do the same thing with subtraction. And again, I said this is for younger children. There are other tools called specifically base 10 blocks that you can explain that same concept to older students, because you can create much larger numbers doing that. But see, then it makes sense because it's not just mechanical. They understand why they're doing what they're doing. Another tool that I used many times as a supervisor, and I said I drew many pizzas on the side of a paste page to explain fractions. You can use, these are called fraction tiles. These come in a variety of arrangements. You can buy them round, so it looks like a pie. So you can use your pizza analogy if you wanted to. You can use them, they're linear like a ruler, but they all explain to a child the fact you can show them that 1 and 2 halves are the same thing, or that 1/2 and 2/4 are the same thing. So they can understand when they're changing to least common denominator that 2/4 and 1/2 are the same thing. You can also illustrate for them when you ask them which is the larger fraction. Well, they can look at the denominator, of course, to determine the larger the denominator, the smaller the fraction. But you can show them graphically that you take these tiles out, they come out of the board here, and show them that 1/3 is actually larger than 1/4. That shows, again, that's why it's the case that it's a smaller fraction, because the denominator is larger, but you can show them physically using the fraction tiles. I even had a supervisor tell me one time that they use fraction tiles with music to show a student that a whole note is 8/8 notes, or a whole note is 4 quarter notes. So you can use them in more than one way. Then one thing that students often have difficulty understanding when they get to 7th and 8th level are signed numbers. Signed numbers are a somewhat abstract concept, and we can explain it looking at the paste page, but sometimes students can see things better, understand better if they're able to walk it out. So I, as a supervisor in the past, I've gone and bought just a simple box of sidewalk chalk. And you go outside on your sidewalk or the parking lot outside your school, and you draw a number line. You put 0 in the middle, and your positive numbers are going to be to the right, and the negative numbers are going to be to the left. And then you're going to have the students, you're going to give them cards, and you say, okay, you are -2. So they go stand on the number line on the sidewalk at -2. Then you say, I'm going to add to that -2 a +6. So now we're adding, so we're going to move to the right on the number line. So they're standing on -2. How many spaces are you going to move to the right? 6. They actually walk it off. 1, 2, 3, 4, 5, 6. Where are you standing now? On +4. Oh, that's a much more graphic illustration for them to understand a relatively abstract concept, especially when they first are learning signed numbers. And then there are many manipulatives that you can use to explain concepts to children, especially young children. Now, all of us have a primary learning style. We are either a visual learner, an auditory learner, or a tactile kinesthetic learner. Regardless of what our primary learning style is, the other two will reinforce what we have learned. I'm primarily a visual learner. Mrs. Dawson is primarily an auditory learner. But many children learn best when they can pick up and hold things. So now you can use, for what I'm about to explain to you, you can use pennies or any other kind of coins. You can use buttons. You can use M&Ms or Skittles, and they get the answer right. They can eat the M&Ms or the Skittles. But then you have to deal with the sugar high later in the day. But these are called attribute blocks. Now, these are in geometric shapes. They are two-dimensional. I mean, technically, you and I know that they have a third dimension, but they are flat. So when they're learning basic geometric shapes, you can show them and let them pick up and hold, this is a rectangle, and this is a triangle. They can feel the difference between the triangle and the rectangle. This is a circle. A circle doesn't have any corners. They can feel the difference as well as see it. You can teach colors with using these. These are several different colors. And then you can also teach relative size. These are both circles, but which one is the larger circle? They can easily see and feel which one is larger. Now, that's two-dimensional geometric figures. But later on, they're going to learn about three-dimensional geometric figures. And they're drawn in the pace, showing the third dimension, but if they're a tactile learner, it's much better for them to be able to pick it up and hold it. So we have these other manipulatives. This is a cone. Now, it's similar to a triangle, but it has the third dimension. So they can pick this up and feel this and see this is different from that because this has a third dimension. This has length, width, and height, not just length and width. And we have cones, and we have cubes, and we have rectangular solids, we have spheres, and so forth. So again, the tactile student can see and feel the difference as well. And then you want to use creative explanations. In algebra, when they are learning how to factor a trinomial, when the coefficient of the first term is greater than 1, many students struggle with learning that concept because it takes a great deal of trial and error. But I want to show you a way that will work every time in factoring a trinomial, even if the coefficient of the first term is greater than 1, that will not require all the trial and error. On the PowerPoint, you can see our equation 2x squared plus 8x plus 6. So you multiply the coefficient of the squared term and the constant. In this equation, you're going to multiply 2 times 6, which is 12. Then you're going to put that answer, that 12, in the right side of a little column, a little table that you have developed. Then you put the coefficient of the x term in the left side of that table. The coefficient of the x term is 8. So you've got 8 at the top and 12 at the top. Then you find the factors of the right term, the 12, that will add up to the 8. Well, there are several factors of 12. 12 and 1, 6 and 2, 3 and 4 are all factors of 12. But 12 and 1, you add those together, that's 13. That won't work. You add 3 and 4 together, and that adds up to 7, so that won't work. But 2 and 6 added together equal 8. So that's the pair that we want to use. So you take your equation and rewrite the problem using those two factors, the 2 and the 6, as the split coefficient of the x term. So as you can see on the screen, 2x squared plus 2x plus 6x plus 6. Then you cut the problem in half. You can see where we have the backslash dividing the problem in half, and you factor each side individually. So on one side we have 2x squared plus 2x, and we're going to factor the 2x out of both of those terms. We're going to have 2x times the quantity, x plus 1. And on the other side of the backslash, we have 6x plus 6, so we're going to factor a 6 out of both of those terms. So we have 6 times the quantity, x plus 1. Then you take those two binomials, the x plus 1, you have it twice, but you're only going to write it once, and the 2x plus 6. So there are the factors of our original term. Our two factors are 2x plus 6 times x plus 1. You multiply those together, and you get the original trinomial of 2x squared plus 8x plus 6. And that required no trial and error. It will greatly reduce the frustration for your students. When it's a large number, that's the coefficient of that first term, they have to try several pairs before they find out the ones that work. This one reduces all of that trial and error. Then another concept that students often struggle a bit with is multiplying binomials. Now they first learn how to multiply binomials as if they were multiplying numbers. They have x plus 2 and they put x plus 1 underneath of it, and they multiply each term. But when they are required to multiply those binomials horizontally, it's difficult for them sometimes to remember the order in doing that. So you can teach them what is called the FOIL method, as you can see on the PowerPoint. FOIL means the first, outer, inner, and last terms. So you can see they multiply the first terms, x times x, and that's x squared. Then they multiply the outer terms, x times negative 7, and the inner terms, x times positive 4, so that's a negative 7x plus a 4x, which is negative 3x. Then they multiply the last term, positive 4 times a negative 7, and that's a negative 28. So those two binomials multiplied together give you the trinomial of x squared minus 3x minus 28. Now, the point of this workshop was to help your students understand math. And when they understand it, they will be much better equipped to be able to do the problems because they know why it works the way they do. You can even use some of these demonstrations that I've talked about in chapel. You can show them the wonder of God's creation using the demonstration of pi, for example, to help them explain why things are the way they are in nature. You can explain mathematically why no two snowflakes are identical. One of the greatest math minds that ever lived was the Italian mathematician Galileo. Galileo once said, "Mathematics is the language in which God wrote the universe." If we want to have our students understand mathematics, we need to make sure that they are fluent in that language. Mathematics is the language in which God wrote the universe. Let's pray. Father, I thank you for the opportunity to share these things with these folks in this workshop. And Lord, I pray that they have learned some tools that they, number one, will enable them to understand the math that they're helping their students with, and they will be able to help the students understand. So it's not just a rote memory, it's not just mechanical, but they will come to appreciate the wonder of mathematics, that they will truly understand what Galileo meant when he said, "Mathematics is the language in which God wrote the universe." And we ask this in Jesus' name, amen.